Hi everyone. Today's session focuses on a critical technical challenge for global applications, time zone handling. Within the Mendix ecosystem, manipulating dates and times can appear simple, but it hides traps that often result in display issues. Without a clear understanding of localized versus non-localized date-time attributes, you will inevitably face unexpected time shifts. We will explore how Mendix manages these data types out of the box, and then present our own robust solution, GeoDate. This system maps events to their specific time zones, guaranteeing that every user sees the accurate time, regardless of their geographical location.
To fully understand our solution, we first need to look at how Mendix handles dates out of the box. There are two primary options. The first is localized mode, which is the default and recommended setting. It's an intelligent system. If a user in Paris enters a time, it is converted to UTC for storage and then automatically adjusted to Tokyo time for a colleague in Japan. It's seamless and highly effective for global collaboration. The second option is non-localized mode. The logic here is straightforward. If you input 10 a.m., the system stores 10 a.m. period. While this may seem simpler for specific business use cases, as we will see in the next slide, this mode hides a technical behavior that can completely skew how data is displayed. Why does non-localized mode pose a problem? It comes down to the internal mechanics. Even though the value is stored as is in the database, Mendix still relies on a Java object, java.util.date, to manipulate and display it. The core issue is that Java cannot process a date without associating it with a time zone. Since non-localized mode lacks specific time zone metadata, the system defaults to the time zone of the server hosting the application. Here's the result. If your server is located in Montreal and you saved 2 p.m., the rendering engine will apply the Montreal offset when displaying the value. Consequently, what the user sees on their screen will differ from what was originally entered and persisted. This invisible but systematic shift is exactly what makes date management so complex.
To make this concept more concrete, let's look at a specific example. Imagine a user schedules an event for July 21, 2025 at 2 p.m. Since they are using a non-localized attribute, they expect 1400 to remain 1400 across the board. At the database level, everything looks fine. The value is stored as is, without any transformation. However, if our application is running on a server located in Montreal, the system will misinterpret the value during the rendering process. The Java engine will take that 1400 timestamp and, by default, apply a -4-hour offset corresponding to Montreal's time zone during the summer, EDT. As a result, the user viewing the page will see 10 a.m. on their screen, even though 1400 was originally entered. This arbitrary shift, tied to the server's physical location rather than the event or the user's context, is exactly why the standard non-localized mode is so risky for data integrity.
To address the shortcomings of the standard system we've just discussed, we introduced the GeoDate concept. The idea is simple yet powerful. Instead of letting the system guess the context of a date, we create an object that encapsulates all the metadata required to define a specific moment unambiguously. A GeoDate doesn't just store the day and time, it systematically couples them with the specific time zone where the event occurs. Why is this a game changer for our application? Because by leveraging this data, the system calculates what we call a UTC Instant. This serves as a universal time reference. The beauty of this approach is that the calculation is entirely location agnostic. It doesn't matter where the user is or where the server is hosted. By doing this, we eliminate any risk of misinterpretation at the source. Let's take a look under the hood to see how this magic actually works. The process follows two key steps. First, the system takes all the inputs, the day, the time, and most importantly, the event's local time zone, to generate a UTC instant. The crucial factor here is the isolation of the calculation. The system abstracts away the surrounding environment. Whether your server is in Montreal or you are accessing the app from Tokyo is completely irrelevant. Second, to make this data database friendly, the instant is converted into a long value. This is simply the number of milliseconds elapsed since the Unix epoch, January 1, 1970. Why bother with such a long number? Because numbers don't lie. Unlike a complex date object that is prone to reinterpretation, a numerical format is universal, lightweight to transfer between systems, and guarantees that the event remains precisely anchored in time.
Now that we've covered the logic behind GeoDate, let's look at how it is persisted at the database level. Instead of relying on a standard date-time attribute, which is vulnerable to system-level misinterpretation, we chose to decouple the data into two separate columns. On one hand, we have the raw temporal value, a long integer representing the millisecond count. Why use a numeric primitive? Because engines process numbers much faster than complex date objects. This makes our sorting and querying near instantaneous. On the other hand, we store the time zone ID as a string, such as Europe/Paris. This is our contextual compass. Without it, we would have a precise point in time, but we wouldn't know if it represented breakfast in Paris or dinner in Tokyo. This combination allows us to reconstruct the exact local time whenever the user needs it.
Why did we opt for this apparent complexity instead of sticking to the Mendix standard? It comes down to three major factors: performance, reliability, and flexibility. First, from a performance standpoint, the gains are significant. Sorting or filtering thousands of long primitives is much lighter for the database than manipulating complex datetime objects. It reduces computational overhead, resulting in an invisible but very real efficiency boost for the end user. Second, we achieve total reliability. When performing conflict detection, for instance, to check if two events overlap, we are no longer comparing time zones, we are simply comparing two integers. It is purely mathematical and therefore error-proof, regardless of the user's geographical location. Finally, this approach gives us full UI flexibility. Since we store both the raw timestamp and the timezone ID, we can format the display exactly as needed, ensuring the data remains firmly anchored in its original local context.
To conclude this technical session, let's discuss the cleaver date or cutoff date. This is a vital concept for maintaining data integrity across our platform. In a distributed global system, how do we fairly determine if a user still has the right to modify a record? If we were to rely on the user's local time, someone in New York might still be able to edit an event that is already considered finalized by a colleague in Paris. To prevent this discrepancy, we implemented a straightforward rule. The cutoff is triggered at the exact start time of the event, based on its own local time zone. Once this threshold is crossed, the system enforces an automatic lock on the data. This ensures that our historical records remain immutable and reliable for everyone, providing a single source of truth regardless of where users are located around the globe.
In conclusion, adopting the GeoDate concept is more than just a technical workaround for a Mendix platform limitation. It is a comprehensive strategy to ensure data accuracy throughout our application. By decoupling temporal data into a numeric UTC Instant and an explicit timezone ID, we have built a system that is both robust and high-performing. We are no longer at the mercy of server or browser timezone settings. We master them to provide a consistent user experience, regardless of geographical location. This approach ensures that our collision logic is mathematically sound and that our historical records are protected by a fair, universal, and automated locking rule.
Thank you for listening. We welcome your questions and suggestions. Feel free to contact us anytime.